Welcome back to the classroom. My name is Mr. Wong. Today we're covering Module 8 from the universe to the atom. We're going to be covering inquiry question 3, the quantum mechanical nature of the atom, and we're going to be investigating 3 dot points here, so there's quite a lot of content to cover through today. Alright, just to start ourselves off, we're going to look at what the Balmer series was and how it helped improve our understanding of the Bohr's model of the atom. We're going to assess the limitations of the Rutherford Bohr's atom, and we're going to then also implement it into what we call Rydberg's equation. There's your textbook links for today. Okay, so let's just quickly talk back on what the Rutherford and Bohr model was. So you can see down here, Ernest Rutherford as well here, that was his model of the atom. You had a centralized nucleus where it was highly densely packed with positive charges, and then you had these electrons surrounding it. Niels Bohr added a second point to it. He also said that there were energy levels of which these electrons belong to, and that these energy levels of the electrons were quantized, so the electrons couldn't just move in and out of the energy shell. That kind of helped explain a couple of things that we'll talk about. Okay, so just a little quick recap that you need to know of the Rutherford's Planetary model. Remember, one of the main issues was how come these electrons being negatively charged and the nucleus being positively charged, how come electrostatic forces don't just kind of bring them together. Okay. Niels Bohr's atom, his main contribution to help improve Rutherford's concept is that these electrons are stationary, or these are in quantized energy state. So this kind of migration of electrons don't really occur in between, and that's why they don't kind of spiral into the nucleus. So this motion of it going in like this, that doesn't work with the planetary quantum states model that we're talking about. Okay, so that's just a quick recap. Now we need to look at the limitations of the Rutherford and Bohr's atomic model. Okay, so firstly let's look at the inadequacies of Rutherford's model. So we know that the positions of electrons were not specified. That was answered by Niels Bohr. Okay, it failed to address the stability of atoms if the electrons were accelerating. So if the electrons were sort of rotating in circular motion, how come there's no emission of electromagnetic radiation? Why is it so stable? The other one we know of is it doesn't explain the hydrogen spectrum. So we're going to look at that in a second. And it also doesn't explain why the electrons don't spiral in. Like we said, 2 points that were sort of specified already. Bohr's model answers that, and Bohr's model answers this one as well, and also Bohr's model answers that one as well. Okay, alright, so we've already talked about the emission of electromagnetic radiation. According to Maxwell, if we have a rotating, or if we have a circular moving electric charge, that is acceleration, so that should emit electromagnetic radiation. That would break the law of conservation of energy if that was the case, because the electrons are producing infinite amounts of energy from nowhere. As we said, hydrogen spectra, this particular model that we have here doesn't really give us a reasoning of how these form. So we need to look at what Niels Bohr did to improve it, and also what limitations were there for him as well. So we understand with the Bohr's model of this specific energy states, the specific gaps between one shell to another. That basically tells us the energy of the photon that needs to be absorbed in order for the electron to migrate up. So either absorption to go up an energy state, or one that needs to be emitted for the electron to come down. Okay, and this obeys the law of conservation of energy because we know that each specific level is quantized. Each specific energy level has a number that you need to have. So if the electron was to come down in energy state, it has to lose electrons. Now, according to the law of conservation of energy, you can't just lose the electron. It needs to be transformed into something else. In this case, if it's coming from high to low, it's emitting electromagnetic radiation. He also said that stable orbits do not emit radiation, meaning by the planetary model or the energy states that we talked about. Again, we said before there were some issues with this, and then he talked about the circular orbits had an angular momentum of this particular equation here. We will look into what that is shortly. But let's firstly look at where the Bohr's model goes wrong. So the first thing is, the limitation is it still doesn't explain why electrons don't, well, it does explain why the electrons don't rotate towards the positive nucleus, so why there's no spiraling into the center. It does explain the hydrogen spectra because of the quantized energy states, but it doesn't explain why electrons going in circular orbit, so if the electrons are rotating around its own circular orbit, why doesn't it emit electromagnetic radiation? That's not explained. There's some other things that the Bohr's model doesn't explain. It doesn't explain these four things here. So spectral line intensity. If you compare these emission spectra, you can see how some lines of specific colors are more faint, and then this line here is a lot more bright. Now, if it's a lot brighter, what that implies is same idea with the quantum model of photons. That means we're producing a greater quantity of photons. Okay, so there's more photons being released here. But if there's more photons, that means this energy transition is more favored. So the question is, why? Why is this energy transition more favored than other energy transitions? That's not explained. The other one we have is hyperfine splitting. So the other one we have here is hyperfine splitting. You can see here you have your main line, so your main red, your main blue. But what we also see is these sort of fainter clusters that are surrounding these really bright lines here. So why do we get this sort of smaller lines, smaller fainter lines next to the big line? Because what we know is the quantized energy state, there should only be one really sharp line of a specific wavelength. Why do we get these sort of fainter ones directly next to or adjacent to the ones that we predicted? The other thing is it doesn't work for larger atoms. So what we mean by larger is literally anything more than one electron in its shell. So anything like helium or bigger, it doesn't work. So you can understand that this model is not really good at doing predictions for you if you can't do anything bigger than one electron. So no prediction can be made if we go to helium and beyond. The other one we have is called the Zeeman effect. So the Zeeman effect is if you have a emission spectra and you expose it to a magnetic field, we get this sort of splitting effect of the spectra. So how come we see this split off or this break off occurring there? Okay, so let's just quickly summarize. If we're talking about the relative intensity of the spectral lines, there's an implication that there's more transitions going with the emission lines. And so one of the issues is Bohr's model doesn't explain why certain transitions are more preferred. The hyperfine splitting is when we have thin little clusters of thin lines next to the main one. Bohr's model only predicts one spectral line because we only expected one specific energy level, so that's not well explained. What we actually do know with the or the Zeeman effect, is actually electrons have an intrinsic magnetic field, so what we call a magnetic spin. And when we expose the electrons to a magnetic field, the splitting effect that we see here is the interaction of the electron's own magnetic field and the magnetic field that we've applied to it. And so that causes this sort of splitting transition that we have here. Okay. Obviously, at the time, no one actually knew of the intrinsic magnetic field that electrons had. That was a couple of years down the track, so there's the reason. The other failure is obviously can't predict for larger atoms, so anything larger than a hydrogen, which if you think about it, there's 100-something elements on the periodic table, so it's not very useful in making those predictions there. What they didn't realize was a thing called electron shielding. This isn't assessed in the syllabus, but electron shielding is where the electrons are trying to repel against each other, and that causes little shifts and changes to the predictions that we make of the spectra as well. Okay, so that kind of summarizes the limitations of the Rutherford and Bohr model of the atom. Next, we're going to actually analyze the person that helped Bohr or justify Bohr's model of the atom. Okay, and this guy is called Johann Balmer, and we call it the Balmer series, which is essentially looking at the emission spectra of hydrogen. Okay, now this goes back to what we talked about absorption and emission spectras. Now, if you recall with the emission spectra, that occurs when an electron from a high energy level comes down to a lower energy level, and due to the law of conservation of energy, because it needs to lose electron to go from a high energy to low energy, it needs to release some type of energy in the form of electromagnetic radiation to allow for that transition to occur. Okay, now what we refer to the Balmer series is the movement of an electron from a high energy state, from 6, all the way down to a low energy level of 2. Now keep in mind, the Balmer series is about visible light, so I'll just write that down somewhere. So the Balmer series is actually referring to, Balmer series is referring to visible light. And if you want to get visible light in this kind of transition, it's from high energy level N coming down to energy level 2. So that's kind of designated that way there. Okay, and so you can see other types of emission spectras. You have the Balmer, which is N whatever to N2. You have the Lyman, so if it's ultraviolet it goes to N1, and Paston's series, which is for infrared, goes to level 3. Okay, so that's the idea that we have there. Okay, so obviously the Balmer series was really important because if the whole concept of quantized energy state is true, then that's where we come up with the prediction we should only get a specific wavelength formula, and that's exactly what we see here. Now Balmer actually came up with an empirical formula to describe these transitions. And what we mean by empirical formula is a formula that's established from experimental results rather than making it up so rather than using it based on making it up based on the theory, you base it on the experimental data that you have. And this is well used for the spectral lines of hydrogen. And so this is the equation we have here. You don't need to know this for the New South Wales syllabus. The reason being there is another equation that we can use, which is known as the Rydberg equation, but we'll look at from there. Okay, you can actually look at the emission spectra of hydrogen. It comes in specific lines, but there's that. Okay, so that kind of summarizes what you need to know about the Balmer series and its contribution to Bohr's model. So the Balmer series' main significance is to show that you can see that there are specific wavelengths of light formed based on different energy transitions, and that pretty much covers what Niels Bohr was trying to say, right? Because Niels Bohr basically said that you get these transitions occur because the energy states are quantized. So that's what we have there. Okay, the last person we're looking at for this particular lesson is Rydberg and his equation. And we're going to look at how he implements the concepts of law of conservation energy to the emission spectra of the hydrogen atom there as well. Okay, so if we actually compare the pair, Johannes Rydberg was developing an equation to describe the spectral lines of alkyl metals. So alkyl metals are group 1 metals, something like lithium, sodium, potassium. He was trying to look at the spectral lines of those, and he came up with this equation here. Okay, now reading Balmer's work, he realized both their models were equivalent. So this equation we have here is also similar to this equation we have here, or they're quite identical. And so in the syllabus that we're talking about, this is the equation we're using when we want to predict the wavelength of the electromagnetic wave that's produced when it's undergone some kind of emission spectra. Okay, so let's just quickly analyze what this particular equation is trying to tell us. So lambda is the predicted wavelength, so the wavelength of the electromagnetic wave that's going to be emitted. Capital RH, that is the Rydberg constant. You can find this on your data sheet. Okay, so I'll just quickly write that down. So found on data sheet or formula sheet. What we have here, that is our final transition, so the final energy level that we're on, and obviously that's our initial energy level that we have there. If we're talking about the Balmer series, then obviously NF will be 2, because as we said, 2 is the final transition that we get for the visible spectra. And then obviously Ni could be any number that we're looking at there. Okay, let's try and do some calculations with this formula. I'm just going to use one example here. So if we substitute, we want to find the wavelength of a transition from energy level 7 to energy level 1. We want to find the wavelength there. We do 1 over lambda, we substitute the value for the constant. So that number would be 1.097 10 to the power of 7. That's our constant. The final stage we were at was N1, so it's 1 over 1 squared, subtracted by where our initial movement was. Our initial was 7, so that's 7 squared there. So complete your working out and put it in the calculator. We have 1 square of, or 7 square is 1 over 49. So the value we get overall is going to be, just plug it into my calculator. So the value we have here, according to my calculator, we have 1074 blah that. Now this isn't the end of the equation because we're trying to find the wavelength, so we actually found 1 over lambda. So the value we got, if we're trying to write it in units, is actually meters minus 1. So obviously you need an inverse or just flip around the numbers. So if we want to find lambda, it's the inverse of whatever we just calculated there. And what you should find, approximately speaking, the value would be, if we inverse that, is 9305, or you could simply write 930.5 10 to the power of 9 meters, which would be equivalent to about 93 nano, or 930 nano. So that would give us 2, 3, 4, 5, 6, 7, 8. So it'll be 9.31 approximately 10 to the power of minus 8 meters. And so that's how you use the Rydberg equation to calculate the wavelength of the atom or the electromagnetic radiation produced from that transition. Okay, answers for these ones here. Alright, so how does this all kind of collate everything together? We firstly said that electron transitions from high energy to lower energy shells are quantized. Okay, so if the electron is to lose energy to migrate down, according to the law of conservation of energy, this loss of energy comes in the emission of electromagnetic radiation. So we know that this energy gap difference is going to be the energy of the photon that we release, and that way we can work out what the frequency of the light is. And so using our understanding of Planck's equation, we can then work out what the wavelength of the wave is, because we know that the speed of light is constant, so that's one way of doing it. Or we can just simply work in a different way. We can work backwards and find the wavelength using Rydberg's equation there. Now the reason why Rydberg's equation is really important is because it provides a significant step in what we now call the first quantum mechanical model of the atom, which was originally developed by Bohr with the quantized energy states. But this gives us a mathematical way to make predictions on the electromagnetic radiation that we will emit. Obviously, there are some flaws in the Bohr's model, and we'll go into other new ways that we see the atom now, but that was the first step where we began implying that the atom has quantum mechanic properties in it. Okay, if you actually want to work out where we get the derivations from Rydberg's equation, it's actually using Planck's constant and using the electron transitions. So you might want to pause it here and have a look. You don't need to know this derivations for the HSC. Okay, some other questions that you can look at. So it says calculate the wavelength of the hydrogen beta spectral line if it gives a transition from here to here. Use the wave equation and Planck's equation to find the amount of energy carried, and then what does this amount of energy represent within the hydrogen atom? Okay, so let's just go through this quickly. So if we want to calculate the wavelength, so it's 1 over lambda, 1.09 10 to the power of 7, and it is 1 over the final, which is 2 squared, minus 1 over the initial 4 square, and the value we get, plug it into my calculator, that value is 2056875. And then so we need to find the inverse of our answer to find the wavelength. And so our wavelength is 1, 2, 3, 4, 5, 6, 7. So it would be approximately 4.86 10 to the power of minus 7 meters there. So that's what we get. The next part we need to find is the amount of energy. So if we know the wavelength, we know that Planck's constant is E equals hf, but we can also write it as h, speed of light, divided by wavelength. So if we substitute Planck's constant in, minus 30, 4 times speed of light, divided that by our equation for the wavelength. The value we should get is 4.09 approximate 10 to the power minus 19 joules. And so according to Niels Bohr, what does this amount of energy represent? That is the energy gap between energy level 4 to energy level 2, and this is the energy transformed from the electron into electromagnetic radiation as our electron transition from N4 to N2. Okay, that's the allowed orbits we have there. You can try some other questions as well. Alright, so that basically concludes what we need to know about the model. Now this summary isn't quite the same summary as what you need to know, but we talked about the Balmer series, we talked about the Rydberg equation, and we talked about how those all link together with the law of conservation of energy and how that links back to what we know of, which is the quantum model of the atom. Okay, so that gives you a nice little introduction of the quantum mechanics side of the atomic theory. The next lesson we're going to talk about is we're going to address the fact of why electromagnetic radiation isn't emitted if the electrons are going in a circular orbit. And we're going to also look at another quantum theory that's applied to the atom, and that is from Edwin Schrödinger. You might know him as the Schrödinger's cat idea, so we're going to explain that as well. Alright, so again, thank you for joining in the lesson. If you have any issues, always rewatch the video. If not, ask some comments below. But always, welcome back to the classroom and see you next time.